So one fellow says the following. He comes and writes and he says, "Can the roads cross each other? Trying to visualize this, but I can't." Yeah, there's very hard to visualize what we're not used to. In other words, in everyday life, things don't go through each other. Period. We're done, right? I mean, the table doesn't go through the chair. And so people say that's our experience. Everyday things, they just don't go through each other. And so that's our experience, and that's why we have a trouble visualizing this. And you won't be able to visualize it. All you can do is say, yeah, it went through. Okay, so the chair went through the rope. Chair went through the table. Imagine that. Just imagine it. Yeah, you can make them go through each other. On paper, you can do it with a movie. You can do anything you want. You can see a rope go through a rope. You can see a table go through a chair. You can see a tree go through a rock. You can do whatever you want on paper, if you're making a movie. Okay, fortunately, technology allows us to do all this stuff today. So if you have trouble imagining it, just do it. Just make a little video showing how a table goes through a chair, and you're done. You are able to visualize it. See how simple it was? And another fellow says, he beat me up. He says the following. He says, "Gideon has conveniently given this specific object the property of intangibility." We have an object that can't be touched. Exactly. The assumption is irrational. And so, yeah, you can't touch the rope. You try to touch the rope, you can't touch it. And they say, how come you can't touch the rope? It's an object, isn't it? It's a thing. And so the answer is, first let's put the corollary, right? Here it is. Neither man nor God can touch the electromagnetic rope. So not even God can touch it, okay? So if you ever tried to touch a rope, if you did touch a rope, it means that you drank a little too much, okay? No, Mother Nature made it intangible, okay, to us humans and to everybody. So yeah, you cannot touch the rope, meaning it doesn't cross, it does cross another rope, okay? The ropes can cross each other without any problem. And people have a lot of problem with that, lots of problems with that. That's one, keeping them from really understanding the theory, because they immediately shun it, they push it away and say, no, that can't be. So they immediately reject it. Well, the answer to that question is that all theories today, all of them have objects going through objects. I don't care what theory you have in your mind. I don't care the one you believe in, the one you propose. Your theory has objects going through objects. And if you say that's not true, it's because you're simply not aware that your theory does that. Okay, so Mother Nature has no other way of doing things. She does have all these invisible, intangible meteors go through each other. And so the reason the question never popped up in anybody's mind about their own theories is because they're always using concepts as objects and objects as concepts. So they go back and forth. They have a dual purpose for every word they use. And so when you have this notion of a field, when you have a notion of a wave, nobody asks the question, can a wave go through a wave? Can a field go through a field? Nobody asks that question, because immediately people say, well, that's a concept, that's an abstraction, that's a mathematical concept of sorts. So the question never pops up. It's only when you say, well, does the rope go through a rope? Yeah, this. And people say, oh, no, that can't be. Now you're having a rope go through a rope? How can that possibly be? But when you say a field goes through a field, people don't even ask the question. They never thought about asking the question, can a field or does a field go through a field? Does an energy go through an energy? Does a time go through a time? Nobody asks those questions. But then the word time is used, gravity is the warping of time. And we transfer the energy from here to there. So you transfer the energy like a ball, and doesn't that energy hit another energy, go through it, or what does it do? And so, again, people never ask the question. The question never popped up in their minds, especially of mathematical physicists. Why? Because they're using concepts. And so they never ask, does a number go through another number? Does a value go through another value? That's the issue. They're using all these abstractions as physical objects when they give their physical interpretation. Then they revert back to the concept. But here, where did I get all this stuff about the rope model? well, this is not where I got it, but here we have some authority for those people who rely on authority. And this is a professor at Berkeley. I always like to show this because it puts it in the right context of what we're supposed to explain when we explain gravity. This is what you're going to have to explain. Okay, if you can't explain this, then you're not doing gravity. Okay, so I don't care if you're doing black holes with the string theories. I don't care if you're doing general relativity. This is what you got to explain. This is the description of gravity. Okay, here it goes. Listen carefully.
If you have the Earth, and it's a big mass here, and you have you, with your little mass here, that every atom on the Earth is pulling on every atom of you. You're also pulling on it. You're pulling on atoms right now on the other side of the Earth. On the other hand, there are a lot of atoms here you're pulling on. You're pulling on all of them. The amazing thing about gravity is it goes right through things.
Okay, now that's something you can't explain with space-time, because space-time is not a pulling theory. Okay, there's no pull. And under quantum, how do you pull? How do you pull with particles? How do you pull with outgoing waves, gravity waves, right? How do you pull between two atoms? For there to be a pull between two atoms, there has to be a physical entity physically binding two atoms. There is no other possibility. And so every atom is connected, physically connected to every atom in the universe. And the only way you can explain that is putting a physical entity between them. And if you put a physical entity between them, boy, you got a big mess, because then the question is, whatever you put in there, it's going to get tangled, or you're going to have to theorize that it goes right through another one of those physical entities that you put as a mediator. That's the only possibility. There is no other logical possibility. Okay? So let me repeat. You need to put a physical elongated, it's got to be elongated entity that physically connects any two atoms in the universe. Okay? If you don't have some kind of physical mediator like that, you're not doing gravity. You're not going to be able to explain gravity, because that is the description of gravity. Okay? So space-time cannot do it. Gravitons cannot do it. None of those can do it. Or whatever, waves cannot do gravity waves. They cannot do it either. You cannot pull with an outgoing gravity wave. You cannot pull with particles, gravitons, discrete ones. And you cannot pull with space-time, because space-time is a push theory. You have to first push the canvas downwards to create the depression. So, yeah, force is involved in general relativity. It's just that they don't talk about that part. It's a little uncomfortable. Yeah, you have to push the canvas downwards, and the question is, why is it being pushed downwards? Or are you pulling on that object, on the mass? Are you pulling it through the canvas, or is the canvas pulling on the mass, right? If it's pulling, by what means? How does space-time, a concept, pull on the concept mass anyways? Okay, so yeah, you can. You have to pull on every single atom, and that's the description of gravity. So just in case, here it goes again. Here's Mr. Muller, Richard Muller from Berkeley University, and what he says that you're pulling on every atom on the other, that makes up the Earth. Okay, and the only way to pull is with an elongated entity that you cannot see or touch. That's the specification you have to meet. If you can't meet that specification, you know nothing about gravity. Okay, that's how simple it is. Okay, so yeah, you can look up the link there. Okay, I put it in there so you can find Richard Muller. He said all these things and he doesn't even know what he said. Because if he would have paid attention to what came out of his mouth, he probably would have figured it out. Okay, so here it is. Here you have every atom of the Earth connected to our astronaut. Astronaut falls to Earth. Why? Because every atom in his body is connected to every atom on Earth, physically connected by elongated entities which have the shape of DNA. Okay, that's why he falls to Earth. They fan out, and as he falls, you have the acceleration of gravity, because more and more ropes are acting independently. We call them effective ropes. Okay, and so that's the mechanism we propose for gravity. There's no pulling in the sense of there's not an elastic. Okay, these are not elastic ropes. In other words, they don't stretch. Okay, as you fall and you're in a new location, a distance closer to the Earth, more and more ropes separate from the coaxial. In fact, here let me illustrate this briefly so that you can get a better idea of what I'm saying. Here it is, the astronaut far away from the Earth, right? And all the ropes come together at infinity, if you understand that word, right? And maybe he weighs 1 pound or maybe a few grams, right? But as he approaches the Earth, the ropes are fanning out. They're coming out of the coaxial, okay? And so now each one is acting independently, and there's tension between any two atoms that connect the astronaut to every atom on Earth. So any two atoms that you pull at random, there's tension. There's no pulling. It's a tension. And at a new location, you have just more ropes acting independently, and it's all under tension. And closer to the Earth, more ropes act. And so weight, you see the weight there changing? It's just a function of distance. That's why gravity is a function of distance. Okay, so there you have the mechanism. Believe it or not, we don't care. Science is not about belief. Science is about understanding. Hopefully you understand the theory we're proposing. Okay, so like I said a minute ago, every theory out there, every single theory on planet Earth, ever invented, ever developed, anywhere that it's been, anytime it's been manufactured, all theories have objects going through objects. And I'll just give you some examples to make my point, to make my case. And we're going to start with space-time. We're going to find out whether space-time is a physical object first. Because if it's a physical object, do space-times go through space-times? Okay, that's what we need to answer. Okay, so first let's make sure we're talking about a physical object and not an abstract concept. Okay, let's bring proof, evidence, to back up our case that space-time is treated at all times as a physical object. Okay, and so this is what space-time looks like. It's a little net, fishnet, canvas, trampoline, I don't know, whatever you want to see it as, right? And they say space-time is gravity is warp time. Okay, that's what they say. If you warp time, you got gravity. And they say that gravity does warp time, so there you have it. Gravity warps time, and that's why we have gravity. Okay, so it's a circular argument. Okay, so there you have it. The reason the moon doesn't fly out of the Earth, right, or out of the solar system, right, is that it's got this wall, this depression that's coming up against the skin of the moon, our satellite, right, and doesn't allow it to fly away. So there's this wall of time, right, that's blocking the moon, this satellite, this rock that rolls around us. That's the explanation. That's a physical interpretation. Okay, and you say, Bill, you're making fun of us. You're ridiculing relativity. No, I'm not ridiculing. Let them do the ridiculing themselves. Here you have testimony of qualified people. Okay, so listen carefully. Here we have it. They'll tell you in their own words. So listen carefully.
I can describe what gravity is doing. I even have a mechanism for it. Gravity really is the curvature of space and time. Movement of matter on that fabric of space and time we call gravity. Why does matter and energy curve space and time? Okay, that's a frontier. We're still working on that.
Okay, so the cause, they're still working on it, okay? So please don't ask. Go to the philosophers on the other side of campus. They'll tell you why. They answer why questions. These folks don't. They just do math, tell you it's the warping of space-time. When you say, well, why does space-time warp? I don't know, ask the philosophers. We're still working on it, okay? Yeah, they'll work forever on that. Okay, so, when you point that out to these people, they get so upset and they come up with this nonsense. They have this cartoon out there that laughs at you because you criticize their carefully formulated theory, right? And it says, understanding gravity, space, time is like a rubber sheet. Massive objects distort the sheet, and they distort it because they're pulled down by what? Very good question. That's the right question. And the professor gets a little upset about that. He says, space-time is like this set of equations for which any analogy must be an approximation. And that's the wrong response, saying boring. No, that's irrational, not boring. That's what it is. That's what we call it in science. We call it irrational. Okay? The guy cannot give you a physical interpretation, so he reverts, says, well, let me show you the set of equations. That's a description. That's not an explanation. So first he gives you an explanation, then he ridicules you because he says, you took my analogy too literally. Yeah, physics is literal because physics is done with objects. It had better be literal. You don't fool Mother Nature. Mother Nature only works with rocks, with atoms. She doesn't know anything about equations, numbers, or anything that humans invented. Concepts, fields, energies. She doesn't know anything about that. She works with objects. She works with atoms, with asteroids, planets, stars, galaxies. That's what she works. That's her world, or Father Universe's world, right? They don't work with abstract mathematical concepts invented by man, which are merely relations that we established with units that we established. She doesn't know what a pound is. She doesn't care about pound or a kilogram. She doesn't care about distances. She doesn't care about time. None of that has anything to do with her or with Father Universe or God or the devil, whoever you worship, right? No, their world is a world of matter, of things. That's what they work with, and that's what you got to figure out. How do they do all these things with things? How do they do all these phenomena with things? Okay, and so is space-time a thing? And here we have some more testimony. Let's put testimony under and make sure everybody understands what space-time is. Okay, how it's treated and how they give physical interpretation using this a thing. Okay, here it is. Okay, listen carefully.
Is space-time real, or just a large-scale illusion? We should think of space and time as a single entity, the physical fabric of our universe, the mathematical object called a manifold. Space-time is a manifold that bends and curves. With this picture of space-time as a unified continuum, Einstein began to wonder about its shape. Let's imagine we're a cat walking on the surface of this manifold.
Okay, is space-time a physical object or not? Well, they treated throughout the exposition, they treated throughout the dissertation as a physical object. And let's give a second one here, just in case, so you know that I'm not pulling something out of nowhere. In fact, all videos that you find show that space-time is a physical object. All papers that you read treat space-time as a physical object. Okay, and here's another testimony. Okay, here it goes. Listen.
This imaginary grid, made up of a multitude of small particles, will allow us to visualize the invisible, the geometry of the universe. The grid is not perfectly static. It drifts very slightly, like a river whose current carries everything with it. The stars, clouds of gas and dark matter, effectively distort space-time, pulling the fabric of the universe in their direction. The universe is constantly expanding. Like a fabric that stretches, the grid swells more and more. The sun curves space-time. Space-time is curved by the Earth and prevents it from moving away. The spin of the Earth affects space-time and very slightly drags the grid along with its rotation.
Now, I just want to clarify that I put all those images in there. Those were not the images they put in there. I just put the images to correlate with what they were saying, okay? So as you can see, they treated, they talk about motion of space-time. They talk about bending of space-time. They talk about space-time being dragged around by objects such as the moon or the earth. They're treating space-time at all times as a physical object. That's the physical interpretation. Like Tyson said, what is gravity? The warping of space-time. What is warp? Are they warping numbers? No, they're warping a thing when they give you the physical interpretation. So yeah, all physical interpretations of general relativity have space-time as a physical object. That is the physical object used. So they can't later on say, oh, but space-time is an abstract concept. No, and that's the reason people say, well, does a space-time go through another space-time? I mean, how many space-times are there? Okay, and here you have a space-time here. Doesn't that look like space-time? A little canvas moving around, a field, they call it, okay? And, if you have one for every particle in the universe has a field, as they say, and you have the gravitational fields of every black hole in the universe, of every sun, every star, right? You have all these space, and you have from every galaxy that's moving around, you have all this motion in the space-time. Do each one of those objects have their own space-time? So if they do, and space-time is a physical object, then how does this happen? Do you have space-times moving through space-times? Is that how they visualize it? And of course, that's when they say, well, space-time is not a physical object, therefore they never ask the question whether a space-time can move through another space-time. Okay, it never popped up because everybody in the back of their mind said, well, space-time is just an abstract concept. Yeah, but they're treating it as a physical object, so they have a dual purpose for this word space-time. They give the physical interpretation saying it's the bending of space-time, and then they, when you say, well, do they go through each other, then they say, well, space-time is really a concept. And that's why they never ask the question whether space-times can go through space-time. These objects can go through objects. Okay? These fields can go through fields. I mean, here you have a field going through a field. Okay, so do fields go through fields? Okay, here you have the famous gravity wave, okay, from two black holes. This was confirmed by experiment. They measured, they detected them. They said it's a done deal. We detected the waves, gravity waves coming from the collision. Really not a collision. They blended. These two black holes blended and became one. See, they don't have them crashing against each other because people would ask, how does a singularity approach another singularity? Do they hit each other? And they say no, so they're friendly. They form a single family and they get bigger. That's all. But see, the waves, they only show this when they try to illustrate it for you. They say, look, all these waves came to Earth and we measured these waves. Well, what if we put a few more in there? I mean, how many black holes are there in the universe? They say there's one in every galaxy, and there's many in each galaxy. And oh, sorry, got the wrong one. Let me get rid of this one. Here you have the gravity waves. Okay, many of them. Okay, so all these black holes, all these waves are going in every direction. Some coming, some going. Okay, and so the question is, how could they measure the collision or the merging of two black holes with so many other black holes sending all kinds of gravity waves, so many stars sending gravity waves, so many galaxies sending gravity? Everything sends a gravity wave along space-time. And so the question is, all this space-time is being kicked around in every direction. We shouldn't be able to receive any gravity waves, smooth gravity waves as just shown, like this shows, like it shows here. We shouldn't be able to see these smooth gravity waves. We would receive something like this in the universe, and in which case, I'm not sure how they can detect that those gravity waves came from the merging of two black holes. Aside from the fact that they never showed two black holes colliding. Why don't they show them colliding? I mean, they're masses, right? Don't masses collide against masses? No. They slowly play this tango, this dance, and they finally merge and form a bigger black hole. That's the way they show those. It's not the way the asteroid that hit the moon, it didn't merge with the moon smoothly. They don't go around and kiss each other and then, kind of blend into each other. No, the asteroid just hits the moon. What was it? The one that killed the dinosaurs, they say, right? The paleontologists. It hit the Earth. It didn't come smoothly and start rolling around the Earth and then become one with us. No, just banged. That's the way they have these things. Okay, so here we have the electromagnetic waves. Waves go through each other. Here's the famous electromagnetic wave. It's smooth. They always show one of them, right? That's fine. Let's show a whole bunch of them. All these waves going around in the universe, don't these waves crash against each other? Or do they go through each other? Because if they crash against each other, not even God would be able to manage this universe. So hopefully they don't crash against each other. They go through each other. And why do they go through each other? Because they're concepts. Because, after all, nobody asks the question for waves. They say, do waves go through each other? And so this is where the problem is. They treat these things as objects on one hand and then to give the physical interpretation. And then they, nobody asks the question, do they crash against each other? Because everybody said, well, after all, we're talking about abstract concepts, abstractions, they're not real things. They're mathematical concepts or whatever. Mathematical objects, as they call them, right? And that's why the questions never popped up. And they only pop up when you talk about the rope. It says, oh, the rope goes through the rope? Oh, how can that be? Well, does your field go through a field? Does your energy go through an energy? Does a wave go through a wave? Does your space-time go through a space-time? That's what you got to ask. So instead of asking me the question, let me ask you the question first, okay? And here we have it with particles. Here you have the world of particles, okay? And you have all these particles around the universe going in every direction. Do these particles bang against each other, or do they go through each other? Okay, so here we have a illustration of that. Okay, do these particles crash or go through each other? Okay, and so that's what you got to tell me. Do particles collide, or do they bounce backwards? Or do they go through each other? That's the question for you. Okay, if you propose particles. So I don't care what you propose. You can propose energy. You can propose fields, whatever. But in the case of particles, it's quite interesting, and you should be aware of this. Here's the version that we have today, the Pauli exclusion principle, right? No two identical fermions can occupy the same quantum state at the same time. So you cannot have two fermions at the same location, period. We're done, right? Fermions, whatever they are, we don't care, right? They're particles. But photons can exist at the same place at the same time. They overlap. Photons are bosons, and force carriers. Bosons were this word invented by bozos, okay? Bozos of quantum mechanics. And so photons, because they're bosons, right, they can not only occupy the same space, they can go through each other. Okay? They can go through each other. It says, in an orbital, a maximum of two electrons, that's the Pauli exclusion principle, two electrons can occupy the same space, and the two electrons must have opposite spins. Okay, that's the Pauli exclusion principle, and it's not a mystery with the rope model because, the thread curls in place all around the electron shell. We call it the magnetic thread. We just label it arbitrarily to keep with convention. We call it the magnetic thread, and it twirls in place as it goes around, the electron shell. And of course, if it twirls in place, the one on the top has to be, if that one's twirling clockwise and it's the same thread that goes all to the other side, the other one on the other side had better be going counterclockwise. So yeah, they can't occupy the same quantum state, as they say. They can't both be clockwise. One has to be clockwise, the other one counterclockwise. Period. We're done. So the rope model explains that Pauli exclusion principle quite well, easily. No biggie. Okay, the other guys simply have to assume, put it as an axiom. They don't know why, but we can justify why. But now we have the opposite view, okay? Here's these people who say, no, that photons collide. These bosons, these bozos, right? They collide against each other. And this is a paper that came out in 1997. And it says that the positrons are interpreted. This is their interpretation, which eventually becomes law, right? Because it's repeated by all mathematical physicists later on, that these things have been proven by experiment that photons collide against photons. Then you have a collision between a high energy photon and several laser photons to produce an electron-positron pair. It turns out that to produce the electron-positron pair, what they did was take virtual photons, as you see at the bottom, right? And with these virtual photons, they created these electron-positron pairs. That's where the magic started. They already had these virtual photons, non-existent photons, unreal photons, right? And from them, they got the electron-positron pairs, which later on from there, they produced these real photons that collided against each other. So this is their interpretation, first of all. Second, they produced it from magic, called virtual photons. And then they violate what we know today, which is that bosons occupy the same location as another boson. So do bosons go through each other or don't they? Do they bounce out? Well, according to Burke and his group, which was about 20 people, right? They decided that photons bounce off each other. Like when you put two hoses with water coming out of them, like two laser pointers, you point them against each other. Well, you don't see the photons bouncing. But if you put two hoses with water coming out of them at great speed, you'll see the water molecules, right, bouncing off each other because they're physical objects. So the question is, can you do that with photons? Well, these people say you can, that they did it in the lab. And so do bosons go through each other or do they bounce? The answer is all of the above. That's the answer today. And just in case, what is a virtual photon? This is so funny because they had to change the definition of what a virtual photon is, okay? Here you have the virtual photon in the year 2000. I had copied it at the time for my book. And look how it's changed till 2024, just 20 plus years, right? Virtual particle is a particle-like abstraction which facilitates understanding of calculation. The term is rather loose and vaguely defined. They appear in calculations, but never as indexes to the scattering matrix. They never appear as the observable inputs and outputs of the physical process being modeled. Their existence is questionable. However, the term is useful in informal, casual conversation or in rendering concepts into layman's terms. And look how that changed. Now, you won't find that in the article anymore. Now you find this. Virtual photons are a fundamental concept in particle physics and quantum field theory that play a crucial role in describing the interactions between electrically charged particles. Virtual photons are referred to as virtual because they do not exist as free particles in the traditional sense, but instead serve as intermediate particles in the exchange of force between other particles. They are responsible for the electromagnetic force that holds matter together, making them a key component in our understanding of the physical world. Virtual photons are thought of as fluctuations in the electromagnetic field. So, are virtual photons real or not? Do they crash against each other or do they go through each other? Well, we'll never know because they created them from electron-positron pairs, which were made from virtual photons. And that's how they do all these interpretations, as they call it, which eventually become law, right? They put them as proof, evidence, okay? And finally, let's look at energy. Does energy go through each other? Well, here you see it, okay? I've illustrated it for you, okay? There you have two energies going right through each other, okay? So don't tell me energy doesn't go through each other. There you see it. The two ghosts go in opposite directions, okay? So if anyone asks you, can energy go through energy? Well, there you have it. Two energies, and they just go through each other as much as they can, right? They don't disturb each other too much, and then they just continue flowing in the opposite direction. Okay, so yeah, anyone who talks about energy, field, wave, space-time, any word they want to use as a physical object has to explain whether that object goes through another object. And all of them do. They have to. There's no way you can run the universe without them going through each other. Particles have to run through particles. That's why the question of whether things go through things is settled. Mother Nature works with things that go through things. And if you don't like it, that's only because you're used to our macro world where things don't go through things. Atoms don't go through atoms. That's how simple it is in our world. But in Mother Nature's world, the one where she uses these invisible, intangible mediators, they do go through each other. There's no other way. There's no way to avoid it. Okay. So whenever you ask whether the rope can go through a rope, yeah, the rope goes right through a rope. And if you say, oh, then I'm going to ask you, what do you propose? Do you propose particles, waves, energy? What do you propose? Space-time, fields? No problem. Do they go through each other?